You know, whether it's the engine in your car or the tools in your workshop, we're surrounded by metal parts that we just trust. We expect them to be incredibly strong, incredibly reliable. But here's the thing, that strength doesn't just happen. It's actually engineered. It's crafted through this hidden scientific process that transforms ordinary metal into something, well, extraordinary. Today, we're going to pull back that curtain.
I mean, really think about it for a second. How does a piece of metal, fresh out of a mold, get the exact properties it needs to handle just immense pressure, intense heat, and all that stress without failing? Well, the answer lies in a super carefully controlled workout, a kind of finishing school for metal.
And that, right there, brings us to the heart of our explainer, heat treatment. And this isn't just about, making metal hot and then letting it cool down. No. This is a highly sophisticated technique that literally changes the metal from the inside out.
So what it is essentially is a series of very controlled thermal exercises. By playing with temperature and time, metallurgists can actually go in and rearrange the internal crystal structure of an alloy. They're basically unlocking its true potential.
I love this analogy because it's just so perfect. A raw metal casting. It has potential, sure, but it's not really ready for the real world. Heat treatment is like the curriculum that trains it for a specific career, whether that's becoming a super tough, impact-resistant gear or maybe a stable, heat-resistant engine part.
Okay, so let's dive into this transformation. How does this actually happen? Well, the journey from just a basic casting to a high-performance part follows a really precise four-step path.
And this just brilliantly shows how methodical the whole thing is. So first up, you've got molten metal. It's cast and it solidifies fast. Then it's annealed. That's a gentle heating process to get rid of any internal stresses from that rapid cooling. Next up is the quench. This is the dramatic part, where the part is heated way up and then plunged into water. This locks in a very specific crystal structure. And finally, a gentle low-temperature heating called artificial aging fine-tunes those properties to perfection. Every single step is absolutely critical.
Now here's the thing. It's not a one-size-fits-all deal. Nope. Depending on what you want that final part to do, you can pick from a whole menu of different heat treatment recipes. Each one is designed to get a very, very specific result.
So this slide lays out what are called the T-types. Think of these like special codes for different outcomes. It's like a recipe book for engineers. Let's say you need a part with the absolute maximum strength possible. Well, you'd spec out a T6 treatment. But what if you need a part that has to stay stable at really high temperatures? That's a job for T7. Each one is a unique combo of heating times and temperatures, all tailored for a specific job.
This is where it gets really cool. Let's just compare two of these to see it in action. You got the T6 treatment. This is like training a powerlifter. The goal is just pure, unadulterated strength. But, just like a powerlifter might not be the most flexible athlete, a T6 part has to give up a little bit of its flexibility, or what's called ductility. On the flip side, you have the TA treatment, which is like training an acrobat. You get more flexibility, more stability, but you sacrifice some of that top-end strength. It's all about these engineering trade-offs.
Okay, so this is a really complex, energy-intensive process. You might be asking, why do manufacturers go through all this trouble? Well, the payoff is just immense. It fundamentally transforms what a metal part can even do. And the crucial point here is that you're not just getting one single benefit. Oh no, it's a whole suite of improvements. You get parts that are way harder, that resist wear, which means they last a lot longer. They can be stronger and more flexible, which prevents those catastrophic failures. They're more stable, so they hold their shape under stress. They're even easier to machine and more resistant to rust. You're basically building reliability and performance right into the material itself.
But here's the catch. This level of control, it requires incredible precision. The whole thing is a super delicate balancing act. If the heating and cooling rates aren't controlled with extreme accuracy, you can actually run into some rare but serious issues, like bubbling in the metal. It just goes to show how scientific and controlled this process has to be to get those amazing results.
So all this brings us to our final takeaway. It's easy to think of working with metal as this process of brute force, hammering and forging. But modern metallurgy, especially heat treatment, is the total opposite of that. It's a game of precision, control, and a really deep scientific understanding.
And this quote from the source material just nails it. The key words here are carefully controlling and exactly to the user requirements. This process lets engineers literally dial in the exact properties they need, custom tailoring a material for its very specific job. It's the science that makes our modern mechanical world even possible.
So, The next time you see a high-performance bike frame or a critical engine component or heck, even a simple, really durable hand tool, you'll know. You'll know its strength wasn't some happy accident. It was forged in fire, precisely controlled, all thanks to the hidden science of heat treatment. So, what are you going to see differently now?